Okay, going through question 2A. Remember, you can go at your own speed, and there may be other ways not shown in this video to arrive at the same answer. So a white light source illuminates a diffraction grating that has 6.30 times 10 to the 5 lines per meter, a lot. The light is normally incident on the grating. Show that the adjacent lines of the grating are separated by a distance of about 0.0016 millimeters, so that approximate about that distance. So what we need to do is, if we know we've got that many lines in a meter, we need to take 1 meter and divide by that number of lines to get the separation. That should give us a figure of 1.58730 blah 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 times 10 to the minus 6 meters. We don't want our answer in meters, we want it in millimeters. Therefore, if we times by 1,000, that will give us an answer of 1.6 times 10 to the minus 3 meters, approximately, which works out at 0.0016 millimeters. Okay, 2b. Well, what we're going to use here is we're going to use the diffraction grating equation. But before we do that, let's have a look at the question. The table below shows the diffracting angles measured from normal for the visible spectral orders using this grating. The angles are given for the red and blue ends of each spectrum, and you can see the figures in the table. We're going to use the first order angle for diffracting the wavelength of red light, which we will find here in the table. Okay, so there you go. We can see that we've got our diffraction grating equation. So if we then put in our values, we've got our distance that we've just worked out between the lines. We're going to use 1.59 times 10 to the 6 in meters this time, not millimeters, because those are the SI units. And then we're going to times by the angle that we've got in the table above. That gives us a wavelength of 6.8 times 10 to the 7 meters, which is approximately 682 nanometers, and red light's about 700 nanometers. So in order of checking our answer, that sounds to be about the right ballpark for our answer. Question B, part 2. Describe carefully the appearance of the complete diffraction pattern on the screen. So remember, we're using white light. You may want to draw a sketch of this pattern to help you explain if you choose. So in the question there was space above the lines so you could draw your diagram of that. Remember, when we're using white light, what happens is we get this diffraction and we get this splitting of the white light at the maximas. The first and second order and third order, if we get that far into the split of the colours. What's important that you need to know is that the zero order maxima is white. Okay, all the wavelengths are there together. We're getting this diffraction happening here due to, if we look at this equation here, which is a rearrangement of the diffraction grating equation, that 400 nanometers, if the distance is, let's just say 1, 1 times 400 divided by 1 is going to be 400. 1 times 700 divided by 1 is going to be 700. So we're going to get that difference in the angle. If we've got the 400 and 700 going to our sine theta, we're going to see that splitting of them. What's important to note is that the blue light is diffracted the less, the red light longer because of the wavelengths, and that's going to happen the opposite way round on the other side of the diffraction, on the other side of the zero order maxima there. And as we move out, they're going to become more and more dispersed, because what we're going to be getting is a larger effect due to the change in the maxima as well, so they can more disperse, more faint as they move along. So a diagram like that would be really useful for you to add to your answer. And the key points are that once we get to third order in this instance, they're going to become more dispersed and start to overlap and fainter away from the centre, but there is that symmetry of the pattern that you can see.